Okay, let's unpack this. I want you to picture a scenario. It's a scenario that I think is going to sound painfully familiar to anyone who has spent time wrestling with Kubernetes, especially if you're doing any of the heavy lifting. You know, machine learning, high-performance computing, that kind of thing.
I think I know where you're going with this. The dreaded pending status.
The dreaded pending, exactly. The purgatory of the cloud.
It's a special kind of hell.
It really is.
Yeah.
So let's set the scene together. You're an ML engineer. You've just finished coding up this massive training job. You're feeling good. The logic is sound. The data is all prepped. You hit enter. You submit the manifest. And this isn't some tiny web server. We are talking about a beast.
Right. You're not asking for a small favor here.
No. You need heavy hardware.
Yeah.
Let's say 8 GPUs, 64 cores, maybe 256 gigabytes of RAM. I mean, you are asking for some serious iron.
You're essentially asking for a specialized supercomputer to just materialize out of thin air.
You are. And the expectation, the dream we were all sold with the cloud, is that you submit this request.
And magic happens.
And magic happens. The cluster just magically scales up, these resources appear, and your model starts learning how to, I don't know, take over the world.
Or, the classic hot dog versus not hot dog.
Right. But that's not what happens. Not immediately, anyway, not in the default setup.
No, it's a lot less magical at first.
Yeah. What happens is silence. Just silence. You check the status. Pending. Wait a minute. Still pending.
You go get a coffee.
You go get a coffee. You come back. You're expecting to see logs just scrolling by.
And nothing.
Still pending.
Wow.
It's just sitting there. The infrastructure is completely silent. And there's this specific emotional frustration in that moment, right?
Oh, absolutely.
It's the feeling of, why isn't the machine listening to me? I have the credit card linked up. I have the code. Why won't you just take my money and run the job?
It is a very specific type of silence. And usually if you dig in, if you do the Kubectl describe pod, you finally see the reason.
Buried in a wall of text.
Buried in a wall of text, you see that one line, 0 of 5 nodes available, or insufficient CP, or the one that really hurts, insufficient nvidia.com/GPU.
Right.
The cluster is effectively saying, look, I hear you, I see your request, but I literally cannot help you. I don't have what you're asking for.
And that is exactly where we are starting today. We are doing a deep dive into the tool that is designed to break that silence. We are talking about Karpenter. But before we get into the how, I want to challenge this idea that it's just better autoscaling. I feel like every tool promises efficiency. Every tool promises to save you money.
They do.
And usually, that comes with a massive complexity tax.
Yeah.
So is this actually a paradigm shift, or is it just a slightly faster way to burn my cloud credits?
That's a fair question. And I would say it is a paradigm shift. I don't say that lightly.
What?
Karpenter is, an open source node lifecycle management project, which I know it sounds boring and corporate.
Lifecycle management. You're right. That sounds like something I'd fall asleep reading in a white paper.
Bear with me. The mechanism underneath, how it actually provisions infrastructure, is fundamentally different from how we've been doing it for the last decade with Kubernetes.
Okay.
The core promise is that it dramatically improves the efficiency and the cost of running your workloads. But the real hook, the mission of our deep dive today, is to walk through exactly what happens behind the scenes.
To resolve that stuck pod.
To resolve that stuck pod scenario, exactly. We need to dissect the mechanics of how Karpenter sees a problem and then actually fixes it. And crucial to that is understanding the difference between the Kubernetes scheduler and Karpenter itself.
Because they are not the same thing. And I think a lot of people, myself included at first, just assume, oh, Kubernetes handles the scheduling, so it must handle the hardware.
They are definitely not the same. And confusing them is where a lot of platform engineers get tripped up, especially when they're starting out.
Okay, so before we get to the hero of our story, let's set the stage with the limitation. Let's talk about the default Kubernetes scheduler. In that nightmare scenario I just described, the stuck ML job, what is happening before Karpenter even wakes up? Why is the default system failing me so badly?
So you submit your pod manifest, the API server accepts it, it writes it into etc., which is, the cluster's brain.
The source of truth.
The source of truth. Then the default Kubernetes scheduler, the standard kube scheduler binary that comes with every single cluster, it wakes up. Its entire job is placement.
Okay.
It looks at your pod, and then it looks at the inventory of existing nodes. It is purely an inventory manager.
It's just checking the shelves in the warehouse.
Exactly. That's a perfect analogy. It looks at node 1. Maybe that's an M5.large instance. It checks the specs. Do you have 8 GPUs? The answer is no.
So it moves on.
It moves on. It looks at node 2. Maybe that's an M5.xlarge. Do you have 8 GTUs? Still no. It goes down the list of every single node currently paying rent in your cluster. And in your scenario, you asked for a very specific, very large piece of hardware. If none of the existing nodes have that hardware available, the scheduler it hits a wall.
And this is the key realization, right? The scheduler is only checking what is there. It has no concept of what could be there.
Correct. It finds no match. So it does its job. It marks the pod as unschedulable. You'll see that condition, pod scheduled, false. And it provides that reason we mentioned earlier, 0 of 5 nodes available. And here is the limitation, the one that defines the need for something like Karpenter. The default scheduler does not provision infrastructure.
It doesn't call Amazon. It's not dialing up Google or Azure.
No. It literally doesn't have the phone number. It doesn't have the IAM permissions. It doesn't have the cloud provider SDKs. It has no logic to call ec2.instances or gcp.instances.insert.
So you should
it just admits failure. It says, I tried to place this person on the furniture we have in the room, and there is no seat available for them. It has no idea how to order more furniture.
Okay, that is a perfect analogy. The scheduler arranges the seating, but it can't buy new chairs. And that total failure, that's the cue, that's when Karpenter enters the room.
Precisely. This is where the baton is passed from the internal Kubernetes logic to an external infrastructure provisioner.
So let's break this down. We've structured this deep dive into the 4 main steps of the Karpenter lifecycle. Watch, evaluate, provision, and result. Let's start with step 1, watch H.
The vigilant observer.
So Karpenter's running in my cluster. It's usually in its own namespace, Karpenter. It's just a pod, right?
That's it.
Controller, nothing more.
Standard Kubernetes controller, yeah. It's just a Go binary running in a pod. And it is running what's called a control loop. This is a tireless piece of software. It never sleeps.
Right.
But the way it sees things is interesting. It doesn't just ask the cluster anything new over and over. It uses a Kubernetes watch.
Okay, break that down for us. Because watching sounds kind of passive. Is it just polling? Is it sitting there asking, are we there yet? Are we there yet? Every 5 milliseconds.
No, and that's a really crucial technical distinction. Polling, just asking, is there a new pod, over and over is incredibly inefficient. It would just slam the API server with requests.
It would be noisy.
Super noisy. Instead, Karpenter uses what's called the informer pattern. It opens a persistent connection, like a long-lived HTTP request, to the Kubernetes API server and says, stream any updates to me as they happen. It's an event-driven subscription.
So it's basically real-time. As soon as that state changes and et cetera, Karpenter knows.
It's milliseconds. But here's the nuance, and this is important. Karpenter isn't watching all pods.
Oh.
If it reacted to every single pod creation event in a busy cluster, it would be absolute chaos. It filters the stream. It is specifically watching for pods that have been marked with that one specific condition, unschedulable.
So it's literally waiting for the scheduler to fail.
Exactly. It's waiting for the system to say, I give up. Going back to our analogy, it's like a taxi dispatcher. The dispatcher isn't worried about the people who are already in a cab or the people who are currently getting into a cab.
They're fine.
They're fine. The dispatcher is waiting for that specific alert that says, customer is waiting on the curb and there are no cars available to pick them up. That is the trigger.
Okay, so the alert comes in, hey, Karpenter, we have a massive ML job stuck in pending. Does Karpenter just immediately go and spin up a server? Because that sounds like it could be dangerous. What if I submit a job by accident and then delete it 2 seconds later?
That is a great point. And you're right. If Karpenter reacted instantly to every single blip on the radar, you'd have this phenomenon called thrashing infrastructure just spinning up and tearing down constantly. It would be a mess.
And expensive.
And very expensive. So it has to filter the noise. It performs a series of checks before it ever commits to spending your money. First, and most importantly, it checks for NodePool matching.
Right, NodePools. We're going to get deep into the configuration of those later because that's where all the dragons live.
Yeah.
But essentially, this is just asking, does this pod match a configuration we've actually set up for Karpenter?
Exactly. A NodePool is a policy. It says, I am allowed to create nodes for, say, the ML team or the web team. Does the pod's node selector, or its affinity rules, line up with a NodePool that Karpenter actually manages?
So if the pod is asking for something Karpenter isn't configured to provide, like, maybe it has some specific legacy label that we haven't migrated to a NodePool yet. Karpenter just ignores it.
It just ignores it. It says, not my problem. The second check is ownership.
Ownership.
Karpenter has a strong preference for pods that are owned by a controller, like a deployment, a stateful set, or a Kubernetes job.
It doesn't like orphan pods. pods that are just created by themselves.
It's risky to provision for an orphan pod.
Right.
Think about it. If you just spin up a naked pod with no owner and that pod dies for some reason, it's just gone. It doesn't get rescheduled.
Right.
So if Karpenter provisions a $30 an hour node for a naked pod that then crashes in 10 seconds, that's a huge waste.
Yeah.
It wants to know that this workload is part of a larger managed intent. It wants to know that a controller will restart it if it fails.
That makes a lot of sense. It wants to back a winner, not a one-off.
And third, and this is critical for efficiency and scale, there is batching.
Batching, like making cookies.
Sort of, like grouping orders together. Karpenter doesn't react instantly to the millisecond a pod becomes unschedulable. It waits a tiny configurable window, usually just a few seconds, to see if other pending pods show up at the same time. This allows it to make a much smarter decision. Instead of launching 10 separate small servers for 10 pods one by one,
it waits to see if it can launch one big server that fits all 10.
Exactly. It's gathering the whole group of people at the curb before it calls the bus. So instead of 10 Uber X's, it can call one Uber XL and save everyone money. It optimizes for density before it even thinks about talking to the cloud provider.
Okay, that's really clever. So it has watched, it has seen the trigger, it has filtered out the noise, and it has grouped the demand. Now we move to step 2, evaluate. This is where Karpenter puts on its detective hat, right? Or maybe its accountant hat.
I like the requirements analyst. This is where the real math happens. And frankly, this is where the complexity explodes, but in a good way. Karpenter performs a deep analysis of the pod spec. It reads the entire YAML specification to build what I call a requirements profile.
So let's go back to our stuck ML pod. It's a beast. What is Karpenter looking at specifically in that YAML?
It starts with the absolute non-negotiables, the resource requests. It looks at the resources, the request section of the manifest. In our example, it sees nvidia.com/GPU 8 memory, 256 GB, and CPU 64.
And those are hard constraints. It can't fudge those numbers. It can't give you 7 GPUs and hope for the best.
No, these are hard constraints. If a potential node type doesn't have 8 GPUs, it is immediately disqualified. It's a no-go. So Karpenter notes this down. A must have at least 8 GPUs, but it also has to account for overhead.
What do you mean overhead?
The node itself, the virtual machine, needs some CPU and memory just to run. It needs to run the operating system, the kubelet, the container runtime, all the system daemons.
The system gets its cut.
The system gets its tax. So Karpenter adds a buffer. It knows if the user asked for 64 CPUs, I actually need a node with slightly more than 64 CPUs available for workloads, or exactly 64 minus the system reserve.
Oh, right. Because if you buy a 64-core machine, you don't actually get all 64 cores for your pod. You lose some to the tax man.
Exactly. And Karpenter calculates that tax internally based on the instance size. But it's not just about raw power. It's also about where and what kind.
The geography and the flavor.
Yep. It then looks at node selectors and node affinity. A node selector is the simpler of the two. It's just simple key-value pairs. For example, maybe your pod has accelerator, NVIDIA Tesla V100 in its spec.
So it's not just give me GPUs, it's give me this specific type of GPU, a V100, not an A100.
Exactly. And Karpenter adds that to the list of requirements. Must be a V100. Then you have node affinity, which handles more complex preferences and rules. A classic example here is topology.kubernetes.io zone. You might have an affinity rule that says, I prefer to run in US-West 2A. Or a hard requirement that says, I must run in either US-West 2A or US-West 2B.
Why would someone do that? Why would you limit your options like that?
Data gravity is the usual suspect, by far. Maybe your training data sits in an S3 bucket in US-West 2 and you want to minimize data transfer costs.
Which can be huge.
It can be astronomical. Or even more commonly, your persistent volume, your EBS drive, is physically pinned to a specific availability zone. You physically cannot mount a hard drive that exists in Zone A to a computer that's running in Zone B.
Physics is a harsh mistress.
It really is. So Karpenter reads that affinity rule and says, okay, cross us East 1 off the list, cross us West 2C off the list. We are only shopping in these 2 aisles.
Okay, that makes sense. What about taints and tolerations? We hear these terms a lot, but I feel like they are often misunderstood. They sound kind of negative.
They're the bypass keys to the VIP room. That's how I like to think of them.
I like that.
Imagine you have a node pool for your GPUs. You don't want some tiny, low-priority web server taking up space on a massive, expensive GPU node just because it happens to fit in the leftover memory. That's a huge waste of money.
For sure.
So you put a taint on that node pool. You might add a taint like nvidia.com/GPU.NoSchedule.
Which is like a do not enter sign for most pods.
Or a hazardous materials area sign. Regular pods see that taint, and the Kubernetes scheduler won't place them there. But your ML pod, in its spec, it has a toleration that exactly matches that taint.
The key.
The key. Karpenter checks for this match. If the pod has the matching toleration, Karpenter knows, aha, I'm allowed to provision a node from this restricted, expensive GPU NodePool specifically for this pod.
So it's basically checking for permission to enter the expensive room.
Yes, and it's also smart enough to check for no execute taints. If a NodePool has a taint that says evict anyone who doesn't have a toleration and your pod doesn't have it, Karpenter knows it can't use that node because the pod would just get kicked off immediately after landing.
So after reading all this YAML, the resource requests, the system overhead, the affinities, the taints, the selectors Karpenter, essentially compiles a shopping list.
A very, very specific shopping list. The output of this entire evaluation phase is a precise list of needs. It's something like, I need a node with 8 V100 GPUs, 256 gigs of RAM, plus system overhead, located in USWest 2A or USWest 2B, that allows this specific nvidia.com/GP taint, and is from an instance family of either P3 or P4.
It knows exactly what it wants. But here is where I get a little skeptical. Knowing what you want is the easy part. Finding the best possible deal for it in a catalog of, 600 different cloud instances? That seems hard.
So computationally hard. It's a variation of the knapsack problem.
Which brings us to step 3, provision, the infrastructure creator.
Yeah.
This is where we leave the abstract world of Kubernetes YAML and hit the hard math of cloud economics.
This is where Karpenter picks up the phone and talks to the cloud provider API, like AWS EC2. But before it makes that call, it has to choose the right item from the menu. And this is the instance type selection phase.
And this is where that efficiency promise really gets tested, because there might be multiple instances that fit the bill.
Almost always, yeah. Let's go back to our example. We need 8 GPUs. Karpenter queries its internal cached memory of the cloud inventory. It might see a P3.16 large that has 8 GPUs, 64 vCPUs, and costs about $24 an hour on demand.
Okay.
But it also sees a P4D.24x large that also has 8 GPUs, but it has 96 vCPUs, and it costs $32 an hour. Both would work for our pod.
Okay, but how does it choose? Is it just looking for the cheapest option that fits? Is it that simple?
It uses a bin packing algorithm, and the strategy is a little more nuanced than just cheapest. Bin packing is a classic computer science problem. How do you fit the most items into the fewest number of boxes to minimize waste?
Bin packing always sounds so tidy, like you're packing a suitcase. But in a cloud environment, you have CPU, memory, GPUs, disk, network bandwidth. It's like multi-dimensional Tetris.
It is multi-dimensional Tetris where all the pieces have different prices attached to them. So Karpenter uses a strategy. It's often called price capacity optimized. It has a hierarchy of priorities. First on the list is cost efficiency.
So it does prefer the cheaper one.
It prefers the cheaper instance if it fits the need. In this case, if the P3 works and meets all the constraints, it will choose the P3 to save you that $8 an hour.
Which really adds up. $8 an hour is nearly $6,000 a month for one machine.
It really does. The second priority is right sizing. It actively avoids gross over-provisioning. If you only request in 256 gigs of RAM, it's not going to launch a node that has a terabyte of RAM unless it absolutely has to. Maybe because that's the only instance type left that has the GPUs you need.
And the third priority?
Consolidation. Remember that batching step? It checks if there are other pending pods, maybe a few smaller ones that got caught in that batching window, that could also squeeze onto this same new node. It's always trying to fill the voids and maximize utilization.
But wait a minute, you mentioned capacity in that strategy name. Price capacity optimized. What does the capacity part mean?
Good catch. This is absolutely crucial for spot instances.
The cheap but risky ones.
Exactly. If you're asking for spot instances, which are much cheaper but can be taken away by the cloud provider with little notice, Karpenter doesn't just look for the absolute cheapest. The cheapest spot instance might be the one that's most popular and therefore the one most likely to be interrupted because everyone wants it.
Right.
So Karpenter also looks at pool depth. It tries to pick an instance that is cheap but also likely to succeed in being provisioned and not get taken away immediately.
So it's checking the likelihood of the server getting yanked away from it before it even buys it.
Effectively, yes. In AWS, for example, it can use the spot placement score as a hint from the cloud provider to balance that risk versus reward.
Okay, that's incredibly sophisticated. So it runs the numbers, it does the Tetris, and it picks the P3.16 Kadrock large. Does it just call AWS immediately?
Not quite yet. There's one more intermediate step. Before calling the cloud API, Karpenter creates a Kubernetes object in your cluster called a node claim.
A node claim? Is this a newer thing? I feel like I remember the term machines or simply nodes from older versions.
Node claim is the successor to the machine concept from Karpenter v0. You can think of it as a reservation ticket.
Okay.
Or a record of intent. It's an object, et cetera, that says, I am trying to create this specific node. It's crucial for two big reasons. One, idempotency.
The $10 word?
It just means handling repeats safely. If the Karpenter pod crashes or restarts right after it decides to buy a node, when it wakes back up, it will see the node claim already exists, etc.
So it knows not to order it again.
Exactly. It sees the ticket and knows, oh, I already ordered this. I don't need to order it a second time. It prevents you from accidentally spinning up 50 supercomputers because of a crash loop.
That is a very, very expensive crash loop.
Indeed. And the second reason is observability. It lets you, the human operator, see what Karpenter is trying to do before the node actually exists in the cloud provider. You can do kubectl, get node claims, and see, oh, it's trying to get a P3 right now.
That's useful for debugging.
Hugely.
Okay, so we have the intent, the node claim. Now, how does it know how to build the node? I mean, which Amazon machine image, AMI, should it use? Which security group? Which subnet? All that plumbing.
That brings us to the node class. You might see this as EC2 node class in AWS or AKS node class in Azure. This is distinct from the node pool. The node pool is the logic, the constraints, the taints, the business rules. The node class is the specifics implementation details for the cloud.
The recipe versus the menu.
That's a great way to put it. The node class defines the AMI ID, or it can be configured to automatically discover the latest EKS-optimized AMI. It defines the subnet IDs, the security groups, the IAM instance profiles, and even the block device mappings for your storage. It tells the cloud provider exactly how to configure the plumbing for the house.
So Karpenter takes the dimensions from the node claim, I need a P3.16 large, and combines it with the detailed blueprint from the node class. And then
finally, the API call. And here's a fun technical fact. Karpenter typically calls the EC2 Fleet API the Create Fleet call rather than the older Run Instances API.
Why does that matter to me?
Create Fleet is smarter and more flexible. It allows Karpenter to pass a list of acceptable instance types, like try a P3.16 large, but if that's not available, a P4D.24 porge would also work, and say, give me the best one from this list that fits my spot strategy. It offloads some of that final mile decision-making to AWS, which has the most up-to-date capacity data.
So it passes the ball to Amazon for the final slam dunk.
Hopefully.
Yeah.
The instance starts booting up, but we are not done. The machine is a blank slate. It needs to know it's part of a Kubernetes cluster. This is the bootstrapping phase.
Right.
Karpenter injects a user data script into the instance launch configuration.
This is like the startup script that runs when the server first wakes up. Yeah. But what is specifically different about a Karpenter bootstrap script?
Speed and specificity. This script does a few things very quickly. It configures the kubelet, the main Kubernetes agent on the node. It applies labels, both the standard Kubernetes ones and specific Karpenter labels like Karpenter.capacity type.spot. But crucially, it applies the taints immediately at startup before the node is even marked as ready.
Why is that so important? Why do it so early?
To prevent scheduler race conditions, if the node joined the cluster and became ready without its taints, there's a small window where the Kubernetes scheduler might see a brand new empty node and try to schedule the wrong pods on it before Karpenter is fully finished. By registering with the taints already in place, it ensures the node is properly reserved for the intended workload from the very first moment it's available.
It reserves the table before it even sits down.
Exactly. And finally, that script tells the kubelet the cluster endpoint, and it joins the node to the cluster.
And once that happens, the node just appears in Kubernetes.
Yes. That's the node registration step. The node pops up in your kubectl get nodes list. And to close the loop, the node claim object is updated to link to this new physical node object.
So we have a node, the hardware is there, the lights are on, which brings us to the final step. Step 4, result.
And this is the part where I have to be very annoying and very precise.
Be annoying. We like precise.
Karpenter does not schedule the pod.
Say that again for the people in the back.
Okay.
Because I genuinely think 90% of people assume Karpenter puts the pod on the node.
Karpenter provisions nodes. The Kubernetes scheduler schedules pods. This handoff is absolutely critical to understand. Karpenter has now done its job. It built the road. Now, the default scheduler, remember the one that gave up at the very beginning, it runs its scheduling cycle again.
It wakes up and checks the inventory again, just like it did before.
It reevaluates that previously unschedulable pod against the now updated list of nodes. And this time, it sees our brand new P3.16 large.
And it checks the specs again.
It runs through the whole predicate check again. Does it have 8 GPUs? Yes. Does it have enough RAM? Yes. Is it in the right zone? Yes. Does the pod tolerate the node's taints? Yes. The match is confirmed.
So the scheduler performs the binding.
It binds the pod to the node. At that point, the pod's status finally moves from pending to container creating and then hopefully to running.
But hold on, there must be a nervous moment there, right? The node comes up. Karpenter thought the pod would fit. It simulated the scheduler. But what if the scheduler disagrees? What if Karpenter's math was slightly off or there was some hidden constraint it didn't account for?
The split brain problem. This can happen, though it's rare with modern Karpenter. Karpenter does an excellent job of simulating the scheduler, but it isn't the scheduler. If Karpenter buys a node and for some reason the scheduler says, no, I still can't place the pod here, maybe due to a weird volume binding mode issue or a complex topology spread constraint, then the node just sits there, empty.
And the pod stays pending. My nightmare continues.
Yes, but Karpenter is watching for that too. It has a process for this. It sees a newly positioned node that's sitting empty. It realizes, wait, I bought this for a specific pod, but that pod isn't here. It will mark that node for consolidation or termination after a short time to live, or TTL. It cleans up its own mistake.
Okay, that's good to know. Let's talk about the timeline here, because we just spent, 15 minutes describing this whole process, but in reality, how fast is it?
It is shockingly fast compared to the old ways of doing things. Let's look at the timestamps. T plus 0 seconds, you apply the job.
Cubic will apply.
T plus 1 second. The scheduler fails, marks it unschedulable. T plus 2 seconds. Karpenter's watch gets the event and triggers T plus 5 to maybe T plus 10 seconds. Karpenter does all that evaluation math and makes the create fleet API call.
So we're only 10 seconds in, and we're already asking the cloud for a machine.
Right. Then you're waiting on the cloud provider. This is the longest part of the process. So T plus 45 to maybe T plus 90 seconds. The node is booted, the OS is loaded, the kubelet starts and joins the cluster. T plus 95 seconds. The scheduler runs, binds the pod, and it starts running.
So we're talking roughly 90 seconds to 2 minutes. From I need a supercomputer to my code is now running on a supercomputer.
Approximately, yes, for a typical VM. Compare that to the old cluster autoscaler, which often took 5, 6, even 7 minutes because it had to update an autoscaling group, wait for the ASG controller to see the update, wait for the ASG to launch the instance. There were just so many layers of abstraction and delay.
We'll definitely get to that comparison in a minute, but first I want to double-click on something we kind of glossed over. NodePools. You call them the way users control Karpenter. But I've also heard some horror stories of people misconfiguring these and getting themselves into trouble.
Yes. This is section 5 of our outline, configuration power, or as I sometimes call it, the how to shoot yourself in the foot section.
Chuckles. Okay, give me an example. How do I mess this up? What's the most common mistake?
By far, the most common mistake is being too specific in your requirements. You set a requirement in your NodePool that says the instance type key must be in the list containing just one item, P3.16x large.
That sounds reasonable, though. I know I want that instance. Why is that bad?
Because you are hard-coding a specific piece of hardware. You've coupled your workload to your infrastructure. If AWS runs out of that specific instance type in ASIS-1, which happens all the time, especially with older GPU generations, your entire pipeline stalls. You've just recreated the exact same rigidity of the old autoscaler that we're trying to get away from.
So the goal is to be vague.
The goal is to be flexible. You should describe what you need, not what you want to buy. Instead of asking for a P3.16x large by name, you should ask for its attributes. Ask for carpenter.k8s.ausinstance-category.p, carpenter.k8s.ausinstance-generation. Or even better, just define the resources. Just say GPU count 8. Let Karpenter figure out the specific model that meets those needs.
Use attributes, not product names. Like shopping for a car by saying, I need an SUV with 4-wheel drive instead of, I need a 2022 Ford Explorer.
Exactly. It makes your infrastructure incredibly resilient to cloud provider stockouts.
Okay, that makes sense. What about limits? Because if I set my NodePool to be super flexible and allow any GPU instance, what stops Karpenter from buying the brand new $40 an hour instances when I only really needed the $2 an hour ones?
2 things protect you there. 1, the bin packing algorithm we discussed earlier always prefers the cheaper one if it fits. But 2, and this is non-negotiable, you absolutely must set limits on the NodePool.
A ceiling.
a hard ceiling. You can set a limit on the total CPU or memory or even the number of GPUs for that node pool. For example, do not provision past 1,000 total GPUs for the ML team. Once that limit is reached, Karpenter will simply stop provisioning, even if there are more pods pending.
It prevents the cloud bill heart attack.
It is the necessary safety valve. I have seen teams forget to set this, launch a massive grid search algorithm that accidentally spawned 500 nodes, and wake up to a $10,000 bill from one night.
Ouch. Okay, so we know how it works. We know how to configure it, or at least how to not misconfigure it. But I want to address the elephant in the room. Before Karpenter, we had the cluster autoscaler, or CAS. It worked, fine for years. Why change? Why is Karpenter considered such a paradigm shift?
It really all comes down to the fundamental architecture. The old way, the cluster autoscaler relied entirely on predefined node groups. In AWS, these were autoscaling groups, or ASGs.
I remember these. You'd have to go into the AWS console or your Terraform and set up a whole list of them.
You did. And the burden was on you, the human operator. You had to guess what your teams might need in the future. You'd create a group for M5.large, then another group for M5.xlarge, then a special group just for P3.16xlarge. You'd end up with dozens of them.
And if you needed a size that you hadn't created a group for?
You were stuck, or you were incredibly inefficient. Let's say you had a pod that needed just a little bit more memory than an M5.large, but you didn't have an M5.xlarge group defined. You might end up stuck in pending, or your pod might get scheduled on a generic large node group that was way too big and wasteful. It led to massive fragmentation and underutilization.
So Karpenter is groupless.
Exactly. That is the new way. Karpenter is groupless. It does not look at a list of predefined static groups. It looks at the pod needs first. It says, what does this specific pod need? And then it scans the entire cloud provider inventory in real time to find the perfect match.
It's just-in-time manufacturing versus stocking a giant, inefficient warehouse.
That is a brilliant way to put it. You get exactly the right size at the right time automatically. You don't need to pre-create and manage all those groups anymore.
And there's a speed advantage there too, right? We touched on this.
It's a significant speed advantage. The cluster autoscaler had to modify the ASG desired count. Then it had to wait for the ASG controller to react, which then had to boot the instance. It was a slow, indirect process. Karpenter calls the Cloud API directly. It just cuts out the middleman entirely.
That adds up when you're scaling up and down dozens or hundreds of times a day. Speaking of scaling down, Karpenter isn't just about adding nodes, is it?
No, and this is where it gets really smart and honestly a little scary for some people who aren't used to it. It is reactive then proactive.
Explain what you mean by that.
It's reactive in that it provisions new nodes when pods are unschedulable. That's what we've been talking about. But once the nodes are running, it becomes proactive. It actively manages the fleet via consolidation, drift detection, and expiration.
Let's talk about consolidation. This is in section 7 of our deep dive. Handling edge cases and disruption. What happens when my big ML job finishes?
Your pod completes its run. The node it was on is now empty, or maybe just has a couple of small system pods on it, like a log collector or a monitoring agent. Karpenter is constantly monitoring for this. It sees this underutilized node.
And it just kills it.
It calculates first. It's a two-step process. First, it asks, can I move these few remaining pods onto another existing node in the cluster that has spare capacity? Or second, it asks, can I replace this expensive P3.16xlarge with a tiny, cheap M5.large now that the heavy job is gone, and move the small pods there?
So it actively defragments the cluster to pack it tighter.
Yes. If it finds a better, cheaper arrangement, it will terminate the expensive node to save you money after safely moving the remaining workloads elsewhere. This is what we mean by disruption. It intentionally disrupts the node to optimize the cluster's cost and efficiency.
But wait. Disrupts. That sounds a lot like downtime. If I have a web service running and Karpenter decides to move its pod just to save $2, does my service go down for a minute?
It shouldn't if, and this is a big if you have configured Kubernetes correctly, Karpenter is a good citizen. It respects pod disruption budgets, or PDBs.
Okay.
If you create a PDB that tells Kubernetes this application needs 3 replicas running at all times, Karpenter will not evict a pod if doing so would violate that rule. It also respects the do not evict annotation you can put on critical pods.
Okay, so it's not a chaotic reaper just swinging a scythe around. It follows the rules of the cluster.
It follows the rules strictly, but you have to set the rules. If you don't create PDBs for your stateful or critical applications, Karpenter will ruthlessly optimize your cluster for cost, and your app might blip during a consolidation event.
That is a very, very important warning. Consolidation requires app-level maturity from the developers.
100%.
What about when things go wrong? Common failure modes. What if the Karpenter pod itself crashes right in the middle of provisioning a new node?
We touched on this with the node claim. That node claim object persists in etc., which is the durable database for the cluster. When Karpenter pod restarts, its first job is to look at all the node claims and reconcile them against reality.
So it checks its work.
It checks its work. It asks, I have a claim for a node, but do I actually have the node in EC2? If not, it will either resume the provisioning process or create a new one. It picks up right where it left off.
And what if AWS is simply out of stock? I asked for a P3.16x large, but Amazon's API returns that dreaded message. Sorry, we're sold out in US West 2A right now. This is the ICE error insufficient capacity error.
This happens constantly, especially with spot capacity or popular GPU types. Karpenter handles this by looking at the other options in your node pool. If you were flexible and allowed multiple instance types, say P3 A and D P4 families, and the P3 is unavailable, Karpenter receives that error from the API, and on its next loop, it immediately retries with the P4.
So it just goes to plan B automatically.
Instantly. It doesn't just fail and back off for 10 minutes like the old cluster autoscaler often did. It iterates through all the allowed options in your node pool in real time until it finds one that works.
And one last detail I found fascinating in the notes. Karpenter has an internal database of instance types. It doesn't have to query the AWS Describe Instances API every single time it does an evaluation.
No, that would be way too slow, and you'd hit API rate limits constantly in a large cluster. Karpenter, on startup, downloads the instance types data, the entire SKU list, from the cloud provider, and caches it in memory. It maintains an internal database of instance capabilities.
Wow.
It knows that an M5.large has 2 vCPUs. It knows the pricing, which it updates regularly. This makes that whole evaluation phase incredibly fast because it's just doing all the math locally in memory without any network calls.
It has the entire cloud catalog memorized.
Oh, precisely.
Okay, we have covered a lot of ground here. From the nightmare of the pending pod to the intricate dance of API calls and the dangers of misconfigured consolidation. Let's try to wrap this up with a summary of the magic.
If you take just one thing away from this deep dive, remember that flow. Watch, evaluate, provision, and result. Karpenter watches for the need, the unschedulable pod. It evaluates and calculates the perfect solution, the bin packing. It provisions the hardware, the create fleet call, and then it hands it off to Kubernetes to finish the job, the scheduling.
And that separation of concerns is just so key. Karpenter handles the hardware, the physical or virtual cloud resources. The Kubernetes scheduler handles the software, the placement of the pods.
Exactly. And the shift in perspective that this enables is massive. We are moving from a world of static infrastructure management, where we as humans manage rigid groups of servers, to a world of dynamic, request-based provisioning.
We aren't really managing servers anymore. We are managing constraints.
That's the final provocative thought I really want to leave the listener with. Reflect on how this completely changes the role of a platform engineer. You stop managing fleets of EC2 instances. You stop worrying about, did I size the node group correctly for next month's traffic? You start managing definitions. You define, this is what a GPU node looks like in our organization, and you let the software handle the inventory and the life cycle.
It really raises the question. If your infrastructure can appear and disappear in 90 seconds based purely on the requirements of your code, what strictly static infrastructure do you actually still need to have running 24/7?
And why are you paying for it when it's idle? If your entire staging environment is only used by developers from 9 to 5, Karpenter can literally delete the entire compute layer at 5:01 p.m. and bring it all back from nothing at 8:59 a.m. the next day, perfectly sized for that day's work.
That is the dream, or the nightmare if your config is wrong. Something for everyone to chew on. Thanks for diving deep with us today on Karpenter.
My pleasure. It was fun.
We will see you on the next deep dive. Keep learning, and always check your YAML before you commit.